Radioactive tracers have been widely employed to study chemical equilibrium and reaction, as well as in chemical analysis. They have been used in various branches of chemistry: organic, inorganic, at basic and industrial levels. The wide potential of radiotracer technique relies on the availability of several isotopic and non-isotopic tracers, thus on the possibility of labeling both elements and chemical compounds, and on the high sensitivity in detection. This last aspect actually makes radiotracer the only method able to investigate distribution processes of chemicals where the concentration at equilibrium goes from very high to very low values. Radiotracers have been used to investigate chemical equilibria. Let's consider the determination of the distribution ratios of iron-59 in a solvent extraction experiment. A hydrochloric acid solution on iron-59 is mixed with di-isopropyl ether in a separating funnel. After separation, the distribution ratio of iron-59 is calculated as the ratio of the iron concentration in the two phases. But iron-59 is a gamma emitter. After separation, an aliquot of each phase is measured by gamma spectrometry in a vial of the same shape and size. The distribution ratio of iron-59 can be calculated as the activity in both the phases. In general, for every separation procedure, if we mark a compound with a radioactive element, its distribution ratio can be determined in terms of activities in the two phases. Moreover, radiotracers have proven to be very useful in evaluating the solubility of poorly soluble compounds. One example are silver halides, such as silver chloride, bromide, or iodide. Silver chloride has a solubility product in water of 1.77 times 10 to the power of -10 at room temperature, which means that about 2 milligrams will dissolve in 1 liter of water. Using silver 110 and silver 111 as tracers, the solubility of halides was determined as a function of the concentration of the corresponding sodium halide. The solubility curves are shown in the image. Starting from water, the solubility decreases with the concentration of halide ions as expected from the solubility product. Then, passing through a minimum, the solubility increases due to the formation of complexes, where the silver ion is bonded with 2 or more halides. The solubility minimum is given by the solubility of undissociated species that cannot be determined with conventional electrochemical methods. Radiotracer techniques have helped study reaction mechanism and kinetics of several organic reactions. In particular, they were advantageous in the case of slow reaction, even taking place in billions of years. Another example of applications is for the determination of the oxidation state of some species in a compound. Let's consider di-lead trioxide. Since oxygen has oxidation number -2, the oxidation number of lead should be +3. Actually, lead has only 2 possible oxidation states, +4 or +2. The experiment was performed by substituting 1 lead atom with the radiotracer lead 210 with oxidation number +2. The formation of the compound with the radiotracer and its decomposition confirmed that lead in the compound has both oxidation states, +4 and +2. By substituting one part of the molecule with the radiotracer, it is possible to elucidate the mechanism of the reaction. The Claisen rearrangement is a powerful carbon-carbon bond-forming chemical reaction. The rearrangement of the allyl phenyl ether apparently does not affect the phenyl group. By adding the carbon-14 radiotracer, it was possible to evidence that the activity involves the phenyl bond, as can be seen in the intermediate step. Isotopic tracers have also been essential in investigating exchange reaction. This application exploits the isotopic exchange of a common component between different molecules or ions. given that the isotopic effect is negligible. The Gibbs energy is the thermodynamic potential minimized when a system reaches chemical equilibrium at constant pressure and temperature. It can predict the direction of the chemical reaction under constant temperature and pressure. Since the isotopic exchange should implicate no change of enthalpy, the entropy term in the free Gibbs energy drives the reaction until the two isotopes are equally distributed between the two reactants. By determining the molar concentration of each molecule and the isotopic species, the reaction rate can be described. Radiotracers are an excellent tool to study the rapid surface reaction between a species in solution and that on a solid, as well as the slower diffusion process in the inner layer of the solid. When a solid is in contact with a liquid or a gas, three processes can be studied by measuring the isotopic exchange as a function of time: surface absorption, surface isotopic exchange, and diffusion from the surface to the bulk. How to proceed? In the case of surface reaction, the solid is put in contact with a solution containing the radiotracers. Then, the two phases are separated and activity measurements are performed. The decrease of activity in the gas-liquid phase indicates the velocity of the process. It is possible to find out the number of absorbed molecules, the kinetics of the process, and the surface area of the solid. As regards to the diffusion phenomena, chemical methods allow observation of diffusion processes only when a concentration gradient is present. Radiotracers enable such limit to be overcome. Indeed, they allow investigation of the cell diffusion of atoms or ions in the solid. In the case of diffusion studies, a thin layer containing the radioactive tracer is formed on the surface of the sample. The system is left in suitable conditions, such as at high temperature for a fixed time. Then, thin layers of samples are removed and the activity is measured. Then, a section is cut vertically and analyzed in order to determine if the diffusion was uniform. Conventional chemistry techniques describe the reaction mechanism by identifying the reaction intermediates, in order of reaction of the reagents, their influence on the mechanism, and the thermodynamic data. Radiochemistry, thanks to the use of radiotracers, enables the expansion of knowledge by highlighting the presence of intermediates even where their quantities are extremely low, verifying the synthesis of processes, and so on. The deeper understanding of chemical processes and phenomena such as solubility, diffusion, precipitation, and also deposition, aging, corrosion, and erosion enable improvement in many industrial processes.